Finally, we're on the last section of chapter 9. So we're going to do 9.10. It's called Using Logarithms to Solve Exponential Equations. So we're going to see some other uses of logarithms to solve exponential equations. So I'm going to reference back to one of the properties that we learned the day before in 9.9, and this will kind of be the whole crux of the lesson, is using this property, that if you have log base b of b to the n, in other words, if these two numbers match, that just equals the exponent n. So don't forget, whenever this happens and they match and you have a log in front of it, it all simplifies to just n. So we're going to first do some problems where we do it without a calculator. We'll do it by hand, and then we'll do some where we're going to use a calculator and actually have to solve these. But first, I'm going to use this property here, this log base b of b to the n, to solve these problems by hand. And then we'll have like a shortcut that we can use to make it a little bit faster. So how to solve this by hand? The way we would figure this out is we would change these bases to the same thing. Whenever we do this with logs, we want to make sure that we talk about the same number. So we want to talk about the same number on both sides. So I'm going to change this to 100. I can change it to 10. That way it matches over here on the right-hand side. 10 squared, because that is 100. Then I just bring down the x with it. So it's 10 squared, so 10 squared times x, or 10 to the 2x. On this side, we already have 10, but I'm going to rewrite it as 10. And if you remember the power when you do this, when you have a square root, that's the same thing as having a 1/2. Now that they're the same, I'm going to use this property up here, log base b of b to the n. So I'm going to put a log on both sides of the equation, and I'm specifically going to choose the base of 10. So I would do log base 10 of 10 to the 2x equals log base 10, base 10 of 10 to the 1/2. So what I'm doing here is I'm putting in a log on both sides of the equation. You're allowed to do that as long as you do it to both sides. And I'm choosing the base of 10. Now, why did I use 10? Because I want these two numbers here to match. So these two numbers match, and what does it equal? Just your exponent, in which case we have 2x. On the other side, we would take this all out, and it would equal 1/2. And the last thing you can do is you can divide both sides by 2. But since I have a fraction over here, I'm going to go ahead and do the reciprocal of 2 over 1. I'm going to multiply by 1/2, which is the same thing as dividing by 2. So multiply by 1/2. So these go away. We get x equals, if you multiply across the top and bottom, you get 1/4. In part B, I'm going to do the same thing, kind of the same idea. I'm going to rewrite 125. We're going to change that to 5 to the, see this says a 5 over here, so I know to use 5. So we're going to have 5 on both of these. The power to get 125 is 3, and I'll bring down the x next to it. On the right-hand side, we'll change this cube root into 5 to the 1/3. And now we can introduce logarithms. So on both sides, we'll have log base 5 of 5 to the 3x. On the other side, same thing, log base 5 of 5 to the 1/3. So this thing keeps happening over and over. We're making them both be the same number on both sides. So that way when we introduce a log, this all goes away, and you end up just getting the exponent. So in this case, we have 3x equals 1/3. This all goes away here. And in order to get x by itself, I'm going to do the same thing I did over here. I'm going to say, well, this is just the same thing as 3 over 1. I'm going to multiply by 1/3. 1/3. There we go. So our final answer here would be 1/3 times 1/3, which is 1/9. And we have one more like this. Remember, we're doing these by hand. There's no calculator for this one. Here we have a 2 and a 4. We're going to rewrite the 4 so that way it has a 2 in it. So I'm going to keep this side the same. So 2 to the x minus 5. And this side I'm going to change to 2 to the, well, how do you get 4? That would be 2 squared x. Bring the x down with it. Now they're the same. Do log base 2 of 2 to the x minus 5. The other side, introduce the log base 2 of 2 to the 2x. All right, so we can get rid of this stuff here, bring down our exponent, and get x minus 5. The other side, same thing. Exponent is 2x. Then it's just a matter of solving this. It's kind of like a algebra 1 problem, most likely. Not too bad. How do we get this solved? We're going to move the x over by subtracting it. So x minus x goes away. We get negative 5 equals 2x minus 1x. Think about it as like this, minus 1x. And 2 minus 1 is 1, so you just get x by itself, and that's our answer. And I forgot to circle this one back here. So hopefully that wasn't too bad. So you can do some of the huddle problems. Specifically, you can do number 1 now. So if I go to number 1, this one here, you can do this one. You don't need to use logarithms, just try to get the same base and solve them. Part A, you would have to change both of them because you can't change this one to a 4. Because think about the powers you're talking about. 4, 16, 64 would be the next one. That's squared to the third. So you're going to have to change both of these. You're going to have to change them both to 2 to some power. The only way to get this to be 4 would be 2 squared. And here you would need 2 to the 5th power. So sometimes you have to change both of them. Anyway, let's go back to the second example. So as we look at these problems, as a shortcut, I think what I'm going to start doing is instead of going from here to logs, I'm going to go from here and just kind of skip the log. What can we do? Instead of writing log out every time, what we're essentially doing is we're getting rid of the base number, in this case 10, and just writing out our exponents equal to each other. So our shortcut, the first one, once you have the same base on each side of the equation, so that would be like all these ones where we had 10, 10, 5, 5, 2, 2. Once we have that, nothing else, we're just going to set the exponents equal to each other. So example 2 says solve the following equation using this new shortcut. So we'll do the same thing we did before, but we're going to skip the log step. I'll show you how. We're going to change 27 into 3 to some power. This side over here will stay the same. How do you get 27? That's 3 to the third. And also bring your x down. So instead of writing logs at this point, we'll skip that step in between, and we'll jump right to the fact that, oh, okay, if we use log base 3, these are going to go away. And then we have 3x equals x plus 8. Now we just have to finish this one. Got to move the x over like we did in the last problem. So I'll subtract x. And we get 2x equals 8. Just divide by 2. And we get our answer. Final answer is 4. Okay, so now since we did this and we did this shortcut, the problem usually arises when we can't actually get them to be the same number. In this case, we had 3 and 3. Can't do it sometimes. So that's whenever we usually use the circle method, if you remember from before, about having to go around the circle. So in this particular case, we have a 7 and 28. There's no way to change this to 7 to some power. Can't do it. Because you're going to get a decimal in this case. So the circle method tells you that you would do log, remember you start with the base, 7, go around the circle, of 28, back to equals x. And then you just type that into the calculator, which I will do as well, but I have to use Desmos over here. So log base 7, 28. I got 1.7124. 7124. Usually do 4 decimal places. But if you don't know how to do the circle method or you forget how to do it, you can also do this new method, which is taking the log. So let's take our original problem, 7 to the x equals 28. And if you get confused with doing the circle thing or you don't like doing it that much, just be more methodical about it. Now we can just throw a log on both sides, which is what I'm going to do. I'm going to put a log over here. I'm going to put a log on this side. But now what we're going to do is use the base of whichever one has the variable. In this case, it's 7. So we're going to do log base 7 on both sides. Put the equal sign between them. And then just bring down the rest of it. So we have 7 to the x, and over here we have 28. So notice what happens on the left-hand side. They're both the same number. We got this multiple times in the last set of problems. When that happens, we start crossing stuff off. It's just the exponent. And what's our exponent here? It's x. And if you notice, this is the same thing that we got over here. Same exact thing. And then we'd put that in the calculator, which we already know the answer, 1.7124. So I just showed you another way of how to solve these problems that if you really don't like the shortcut method or the circle method, going around the circle, then you can do it this way. For the rest of this lesson, I will be doing this new method. But in the future, if you want, you can just use whichever one you want. But some people like this one better. Okay. As a second shortcut, when we're doing this here, and we're doing logs, you're going to take the log on both sides like we did before, but how do you choose what base to use? It's always with the exponent. So 7 to the x here, we want to use log base 7, so that way we bring this exponent down. The whole point is to bring it down as just x. So shortcut number 2, when taking the log of both sides of an equation, just use the log with the same base that is attached to your variable. So let me give you an example. When we go to example 4, we're going to use this new shortcut here when we solve. Instead of doing the circle, I'm going to choose to do a log on both sides. Give myself some space with an equal sign between them. And the base that we're going to choose here is whichever one has the variable on it, which is going to be 3. So I'm going to do log base 3 of 3 to the x. The other side, log base 3 of 243. And then on the left-hand side, as you know, we keep seeing this. This part, I guess you could probably just get rid of. If you can recognize it, just make it x right away. And then the right-hand part, you'll put in the calculator, which I think is the number 5. All right, part B and C, we have some extra stuff to do, but they're not too bad. So for part B, we're going to move the 9 first before we introduce logs. We want to make sure it kind of looks like part A first. So it's minus 9 on both sides. So we get 5 to the x equals 25 minus 9 is 16. Then you're going to do log on both sides. Log, and our base is going to be what? 5. So log base 5 of 16 on the other side. So again, the left-hand side goes away. You just get x, which is what we want. The right-hand side, you'd have to use the calculator, so I will type that in. And we get, looks like 1.7227. If you got 4 decimal places. Okay, last one, and then you should be able to do everything in the huddle besides the one word problem we have to go over. Part C. So how do we get this solved? Don't want to do logs yet. We have this fraction bar we have to get rid of with a 2 on the bottom. And how do you get rid of division or a fraction like this? We're going to do the opposite of division and multiply. So I'm going to multiply both sides by 2. That cancels those out. You get 11 to the x minus 4 equals, multiply them together, you get 1331. Now we can introduce logs. Essentially, you know what's going to happen, right? We need to use log base 11. So if you want to just write the exponent out, we know what's going to happen, right? We're going to get just the exponent On the other side, we need to write out what our log is. Log base 11, 1331. Whoops. Put the right-hand side into the calculator like we've been doing. So we get x minus 4. And I believe that is 3. No decimal in that one. And then we add both sides, 4 to both sides. So I'm going to get 7. And that's it. So all the things we've done so far should take you through how to do number 1 and number 2. Number 2 is what we just talked about. 3 and 4 are word problems to finish it up. So we will go ahead and do a word problem. Change colors, maybe. How about that? All right, example 5. At what rate of interest, okay, or interest rate, I guess you could have said, compounded continuously, do you have to invest your money so that it will double in 12 years if you had $3,000? And we're going to use the continuously compounded interest formula, PERT, A equals P, e to the RT. So let's start with that, and then we'll figure out what to plug in here, PERT. Now, as we read through this, we got to go ahead and figure out what to plug in for each variable, which I put over here, kind of like a fill-in-the-blank thing so you can figure it out. Let's just go through each one and figure it out. So we have T. That would be probably, if you remember, our time. And our number of years is 12, so we'll fill that in as 12. R is what rate you're given. So what's our interest rate? I don't see one. That's what we're finding. At what rate of interest? We do not know R. Question mark. I don't know. P is how much money you initially put into the account or invest. It says if you had $3,000 that we're going to put in, so we're going to start with 3,000. And then A, we hopefully have A because we're already missing one variable. We don't want to miss multiple variables. A would be the final amount that we want to get. So where does it say that at? You have to invest your money so that will double in 12 years. So if we want to double our money and we started at 3,000, think about how you'd figure that out. We're going to take $3,000 and just basically double it, which would be essentially multiplying by 2. We want to have eventually $6,000. Now we have everything we need, and we're solving for R. So on the left-hand side, we have 6,000 equals 3,000. Remember, E is not a variable, it's a number. It's actually 2.71. To the R times T. So R times, we don't know R. T, we do know, is 12 years. So we've used this formula before, but we've never actually solved for R, or we've never solved for anything in the exponent that's up here. But now with logs, we know how to do it. So first thing I'm going to do is not use logs yet. I'm going to move this 3,000 over by dividing it on both sides. That would give you just 2. The other side crosses out. So we get e to the r times 12. I'm just going to make that 12r. Now we're ready to use logs. And you kind of have a choice here. The base that we have to use to bring this 12r down is right here, e. So we're going to use log base e. Although, if you remember what log base e is the same as, you can use that too. It's the same as saying ln. So these two are the same, right? Exactly the same. So it doesn't matter which one you use. You could use ln. Heck, maybe I'll just even split it. I'll use ln over here. ln of 2. On this side, I'll use log base e of e to the 12r. It might be easier to do log base e just so you can see how it matches like it always does and how this goes away, right? So we get 12r equals, now this one you have to type in ln of 2, or you could type in log base e of 2. So ln of 2 is, we're going to have 0.6931. Now you're almost done, but not 100%. We need to divide both sides by 12 to finish it off. Nice. And we would get, I got 0.0577. That's good enough, right? 0.0577. That's 4 decimal places. So this would be your rate that you would need, although it's not as a percentage, so I'm going to go ahead and change that too. So as a percentage, we've moved that over twice. That would be about 5.7%. Or 5.77%. Doesn't matter. It's pretty close to 6%. So if you were to get close to 6% interest rate, you would double your money from $3,000 to $6,000 in 12 years. Which I know would take a long time. 12 years is a long time to only get $3,000 extra, but you're going to double your money in 12 years. That's at 6%. Obviously, if you got more, it wouldn't take as much time. So that one correlates directly to number 3 about Jessica's college savings, where you're going to use PERT again. I'm not going to go through it, but whoops. It's PERT again. And then number 4, you're using this old formula we used a while ago, but same idea. We're going to have to use logs eventually. And you're solving for how many years? So you're trying to solve for t. And then after that, that's the end of the lesson. And there is a homework sheet that goes with this as well, if you were assigned the homework. But that is the last section of Chapter 9, and we're done with it.